Hello, in this video we will look at a couple of distributions where the random variable is a continuous random variable. The first of the distribution is the uniform distribution, which is one of the most simplest distributions, and this is denoted usually on an interval a and b on the real line, where a and b are two constants. A random variable x with a uniform distribution is denoted by this symbol u of a and b. The probability in this random variable is usually proportional to the length of the segment. So we can consider the probability distribution for this uniform random variable as a constant if x is between a and b, otherwise it's 0. Now you can easily find the value of c by using the probability of the PDF, which is the PDF integrates to 1. So by replacing f of x by the constant c, we can easily determine c to be 1 over b minus a. So the PDF for a uniform random variable is 1 over b minus a when x is between a and b and 0 otherwise. The uniform random variable looks like a rectangle over the interval a and b because the probability is constant 1 over b minus a over the interval. We can also calculate the cumulative distribution function for the random variable, which is integration of the PDF over the interval minus infinity to x. So the PDF is 1 over b minus a integrated from a to x because the lower limit is a, and this is x minus a over b minus a. The expectation or the mean for a uniform random variable is integration over the limits a and b for x divided by b minus a. So this will give you a plus b over 2. For the variance, we need to calculate expectation of x squared, which is again this integration of x squared divided by b minus a over the interval a to b, which is b cubed minus a cubed divided by 3 times b minus a. So by substituting e of x squared and the mean in this equation, we can calculate variance of x, which is b minus a whole square divided by 12. Some of the highlights of the uniform random variables are it's one of the most random of their distributions because the probability is constant over the entire segment length. So all the values of x are equally likely. And the uniform distribution is generally used to generate any other distribution. So if you take a random variable x which is uniform distribution, then we can transform that to any other distribution that we may want. Another property, if x is uniform over the interval 0 to 1, then 1 minus x is also uniform over 0 to 1 by symmetry. The linear transform of a uniform random variable is also a uniform random variable. So if you take the random variable x which is uniform, then y is equal to ax plus b will also be uniform on some interval. Non-linear transform of uniform random variable is not generally uniform. The next continuous distribution we'll look at is exponential distribution, which is used in disciplines like engineering, physics, chemistry, finance, and so on. It's generally used for queuing and product reliability applications. For example, queuing example is waiting time between events such as arrivals or time to failure of a component. The exponential distribution has a rate parameter lambda, and the PDF is given by lambda e to the power minus lambda x when x is greater than or equal to 0, 0 otherwise. So the distribution only exists for positive values of x. We can easily test if this is a valid PDF by integrating the PDF over the interval 0 to infinity, since x is only valid for positive numbers, and we've already done this integration before where e to the power minus lambda x, when you integrate, you get the lambda term, 1 over lambda term, and that cancels the lambda to get 1. The exponential random variable looks like this depending on the parameter lambda, and it's a continuous distribution. You can easily calculate the CDF of an exponential random variable by integrating the PDF over the interval 0 to x, and that will result in the CDF 1 minus e to the power minus lambda x. The expectation can similarly be calculated by multiplying the PDF with x and integrating over the limit 0 to x or 0 to infinity. And here we have to use integration by parts, and by using that you can see that the expectation of an exponential random variable is 1 over lambda. Similarly, variance of x can be calculated by first calculating expectation of x square, and here again we have to use integration by parts to get the answer 2 over lambda square. I'm not showing the details of the calculation, and the variance can now be calculated by subtracting the mean square from the expectation of x square. So 2 over lambda square minus 1 over lambda square result in the variance of 1 over lambda square. So for an exponential random variable, the expected value is 1 over lambda and the variance is 1 over lambda square. The exponential random variable has a very important property called the memoryless property, which means that irrespective of the time elapsed, the probability that x is greater than some time interval s plus t, given that already time s has elapsed, is the same as probability of x greater than or equal to t. So if we consider an example, let's say there is an event of getting emails for a particular person. So if the rate is 20, then if you have waited for, let's say, 10 minutes, then the probability that you have to wait 10 more minutes, it is not affected by how long you have waited. So that's what this means. So the probability that you have to wait t minutes longer doesn't matter how long you have waited already, which is s. The proof is pretty straightforward. So the probability, if you use conditional probability definition, the probability of x given x is greater than s is the joint probability divided by probability of x greater than or equal to s. Now this reduces to x greater than or equal to s plus t divided by probability of x greater than or equal to s, which can be written as the complement form, and by substituting the CDF for the random variable, which is exponential, we get e to the power minus lambda t, which is the same as probability of x greater than or equal to t. In fact, exponential distribution is the only continuous memoryless distribution, and if a continuous random variable x has the memoryless property, then that has to be a exponential distribution. So it's a very important property. That's why exponential distributions is widely used in many different fields. That's it for this video. Thank you.